You are correct in stating that utilizing the equipment grounding conductor, or EG, as the neutral for the secondary transformer makes it a current carrying conductor. The National Electrical Code, or NEC, requires the neutral conductor to be insulated in size appropriately for the load, requiring a ground rod poured within the footer and connected to the secondary transformer's neutral, so is a valid safety measure. This measure ensures the neutral remains isolated from the primary EGC and reduces the risk of electric shock in the event the primary EGC is lost. Temperature rating of a transformer indicates the maximum temperature that the insulation can withstand without degrading. The NEC requires that transformers be operated within their temperature rating. A high internal temperature, such as 210 degrees, is concerning. Such a high temperature can indicate that the transformer is overloaded or operating in an unventilated environment. This could potentially shorten the life of the transformer or even pose a fire hazard. The observations and concerns regarding the electrical designs of the airport boarding bridges are valid. The use of the EGC as a neutral conductor is a safety hazard, and the high operating temperature of the transformers is a potential problem. Requiring a secondary ground rod and isolation of the neutral is a reasonable and necessary safety measure. It is important to work with the electrical engineers responsible for these designs to ensure that they meet all applicable codes and safety standards. Considering the use of a 480-volt, 3-phase, 4-wire with ground service to power the passenger boarding bridges, or PBBs, and the inclusion of a secondary transformer within the service disconnect to supply 208/120 volts for lighting, heat, limits, and drive movement raises several crucial points that must be addressed from a safety and code compliance perspective. Firstly, the function of the equipment grounding conductor, or EG, is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. The NEC, specifically Article 250, outlines the requirements for grounding and bonding to ensure electrical safety. When the secondary of the transformer derives its neutral from the equipment grounding conductor attached to the frame of the boarding bridge, it essentially transforms the EGC into a current carrying conductor under normal operating conditions. This is a direct violation of NEC 250.6, which prohibits the use of the EGC as a neutral conductor. This practice can lead to several dangerous scenarios. Firstly, it can cause unwanted current flow on the EGC, potentially creating elevated voltage potentials on metallic parts of the boarding bridge. This can result in electric shock hazards to personnel who come into contact with these parts. Secondly, it compromises the integrity of the grounding system, making it less effective in clearing ground faults. In the event of a ground fault, the elevated impedance of the EGC compared to a properly sized neutral conductor can impede the flow of fault current, delaying or preventing the operation of overcurrent protective devices. Regarding the practice of installing a ground rod within the footer of the passenger boarding bridge, or PBB, and connecting it to the secondary transformer's neutral EXO while isolating it from the primary EGC, this measure is aimed at creating a separate grounding electrode system for the secondary side of the transformer. While this approach is well intentioned, it is crucial to ensure that it complies with NEC requirements. NEC 250.30 provides guidelines for grounding separately derived systems, such as transformers. It mandates that the neutral point of the separately derived system be grounded, and that the grounding electrode conductor be connected to a suitable grounding electrode. The NEC permits the use of a ground rod, pipe, or plate electrode, but it also requires that it be supplemented by an additional electrode if the ground rod is the sole grounding electrode. This additional electrode can be the building steel, a concrete encased electrode, or a ground ring. Furthermore, it is essential to ensure that the impedance to ground from the separately derived system is sufficiently low to facilitate the operation of overcurrent protective devices. The NEC mandates that the grounding electrode conductor be sized appropriately based on the size of the derived phase conductors. The practice of isolating the secondary neutral from the primary EGC is generally acceptable, as it prevents circulating currents between the two grounding systems. However, it is critical to maintain a low impedance ground fault path on both the primary and secondary sides of the transformer to ensure proper operation of overcurrent protective devices. The high operating temperature of the transformer, reaching 210 degrees internally, is a significant concern. Transformers are designed to operate within specific temperature limits typically specified by their insulation class. Exceeding these temperature limits can accelerate the degradation of the insulation, reducing the transformer's lifespan and increasing the risk of failure. The NEC requires that transformers be installed and ventilated in accordance with their listing and labeling. If the transformer is operating in an unventilated disconnect, it is essential to ensure that the enclosure is adequately sized to dissipate heat. Furthermore, it may be necessary to provide forced air cooling to maintain the transformer's operating temperature within acceptable limits. It is important to verify that the transformer's temperature rating is appropriate for the ambient temperature and load conditions in which it is operating. If the transformer is consistently operating at elevated temperatures, it may be necessary to replace it with a larger unit or one with a high temperature rating. UL listing of a transformer indicates that it has been tested and certified to meet certain safety standards. However, UL listing does not guarantee that the transformer will operate safely under all conditions. It is the responsibility of the electrical engineer to ensure that the transformer is properly applied and installed in accordance with its listing and the NEC. In summary, the electrical design of airport boarding bridges presents several challenges that must be addressed to ensure electrical safety and code compliance. The improper use of the EGC as a neutral conductor, the installation of grounding electrodes for separately derived systems, and the operating temperature of transformers are all critical considerations. It is essential to work closely with electrical engineers, contractors, and inspectors to ensure that all electrical installations meet the requirements of the NEC and other applicable standards. The NEC is updated regularly to reflect new technologies and best practices. It is essential to stay current with the latest edition of the NEC and to apply its requirements consistently and correctly. There is also the importance of proper coordination between the various trades involved in the installation of airport boarding bridges. Electrical engineers, mechanical engineers, structural engineers, and contractors must work together to ensure that all aspects of the installation are properly integrated and coordinated. Furthermore, it is essential to conduct thorough inspections and testing of all electrical installations to verify that they meet the requirements of the NEC and other applicable standards. Inspections should be performed by qualified and experienced electrical inspectors who are familiar with the NEC and other relevant codes and standards. Testing should be performed using calibrated instruments and in accordance with industry-accepted practices. One should consider performing regular maintenance and testing of electrical systems to ensure their continued safe and reliable operation. Maintenance should include visual inspections, cleaning, tightening of connections, and testing of protective devices. Testing should include insulation resistance testing, ground impedance testing, and overcurrent protective device testing. Furthermore, documentation should be kept on file: all electrical design calculations, installation drawings, inspection reports, and testing results. This documentation can be valuable in troubleshooting problems and in demonstrating compliance with applicable codes and standards. One additional consideration is the use of surge protection devices, or SPDs, to protect sensitive electronic equipment from voltage surges caused by lightning or other events. SPD should be installed at the service entrance and at any other locations where sensitive electronic equipment is located. There are various types of SPD available, and the selection of the appropriate SPD depends on the specific application and the level of protection required. Also, one needs to consider the use of arc flash protection. Arc flash is a dangerous phenomenon that can occur when there is a fault in an electrical system. Arc flash events can cause serious burns, injuries, and even death. The NEC requires that electrical equipment be labeled with arc flash hazard warnings. Employers are also required to provide arc flash training to their employees who work on near energized electrical equipment. There are various methods for reducing the risk of arc flash, including using arc-resistant equipment, increasing the working distance, and wearing appropriate personal protective equipment, or PPE. One should also ensure the correct use of personal protective equipment, or PPE. PPE is designed to protect workers from electrical hazards such as shock, arc flash, and burns. PPE includes items such as insulated gloves, safety glasses, and arc-rated clothing. It is essential to select the appropriate PPE for the specific task being performed and to ensure that it is properly maintained and inspected. Regular training should be provided to workers on the proper use of PPE. Also, one can consider the selection of electrical equipment. Electrical equipment should be selected based on the specific application and the environmental conditions in which it will be operating. Equipment should be listed by a recognized testing laboratory, such as UL, and should be installed in accordance with the manufacturer's instructions and the NEC. The NEC provides specific requirements for the selection and installation of electrical equipment in various types of occupancies. Also, it is important to implement a safety program. A comprehensive safety program should be implemented to address all aspects of electrical safety. The safety program should include written procedures, training, audits, and inspections. The safety program should be tailored to the specific hazards present in the workplace. Employees should be actively involved in the development and implementation of the safety program. One last point is maintaining good communication. Effective communication is essential for ensuring electrical safety. The electrical engineers, contractors, inspectors, and workers must communicate effectively to identify potential hazards and to coordinate work activities. Regular safety meetings should be held to discuss electrical safety issues and to reinforce safe work practices. By addressing these considerations, one can significantly improve the electrical safety of airport boarding bridges and other electrical installations.